Okay, let me get started here. First of all, are there any questions about projects or stuff that we covered last class? We've been a quick review of linear algebra, which I want to finish today, and then get on to linear regression. Any questions or comments or anything like that before I get started? Okay, what I'd like to talk about today is to finish up the unit on linear algebra. I want to talk about this idea of kind of matrix compression, okay, or the fact that we have data representations and that we can if you have a matrix of n rows and m columns. It would be great if we could represent this by n rows and k columns, where k is much less than n. There are a couple of different ways of doing that. The first, last class we started talking about eigenvalues and eigenvectors. This was remember the equation governing, this kind of notion. If you have a matrix M, okay, you have an eigenvector and its associated eigenvalue. The matrix times the vector is equal to the eigenvalue times the vector. So together, the eigenvalue and the eigenvector has to tell you a fair amount about the matrix. That's kind of the intuition that I have here. One interesting property of eigenvectors, eigenvectors and eigenvalues, is that we can represent symmetric matrices. Okay, n by n symmetric matrices can be decomposed into the products of eigenvectors. Okay, so let's just try to parse this thing. It should be clear that if we have a vector that is n by 1, and we multiply it by its transpose, which would give us a 1 by n vector, we end up getting an n by n matrix. Okay, that's what we call the outer product of vectors. Okay, you guys are used to the inner product, which is what happens if I take a 1 by n vector and I multiply it by basically itself, its transpose, n by 1, I would get a 1 by 1 vector. That's a dot product, okay? But the outer product is one that gives me an n by n matrix. Eigenvector vectors we showed can be computed on any n by n matrix of rank n, okay? You can get the decomposition. One property of it is that if you're given a symmetric matrix, okay, that means that m of ij equals m of ji, then that matrix can be written as the sum of the outer products of all the eigenvectors times the appropriate eigenvalue, okay? So this gives you a way to take that any symmetric matrix that's n by n and decompose it into the products of the eigenvectors. Now, what's interesting about, any questions about that? What's interesting about it, though, is that what we end up getting is we're now expressing the matrix as the sum of n things, and the importance of each thing is kind of governed by the eigenvalue. Okay, there's a coefficient times the matrix. The eigenvalue, the larger eigenvalues, represent the part of this matrix, the bigger contributions to what M looks like. So what's the advantage of that? Suppose, let's say, I have a symmetric matrix, and the symmetric matrix that we all know and that we talked about last time were the covariance matrices. Okay, an example of a symmetric matrix was a covariance matrix. where ij was representing kind of the how in sync row I and j and column j is, row I and column row I and row j is. Because it was symmetric, the covariance matrix ij is the same as ji, so it's symmetric. What you could do, though, is if we sum up the, if we do one of these eigenvector decompositions, if we sort all the vectors based on what their eigenvalue is, from biggest to smallest, as we add more and more of these vector products in, we're going to get a closer and closer approximation to M. And what this is kind of showing you is this is the covariance matrix of the Lincoln Memorial, which is what we talked about before. And this is showing the error vector. What is the difference between the original covariance matrix and what we get after summing up the outer products of the first 5 and the first 50 eigenvectors for these n by 500 images. And what you end up seeing is that the errors are relatively strong at first. But when you start adding more and more of these things, the error, becomes kind of a uniform noise, okay, over the matrix. And so this is an argument that instead of representing an image as a 512 by 512 thing, if we represent the image by a 512 by 50 thing, there is relatively little error in it, okay? And we've done the kind of matrix compression that we like, okay, to give us a denser feature representation. Any questions about that? Okay, so this eigenvector value decomposition is a good way to do kind of dimension reduction, okay, if we have a symmetric matrix that we are given. Any questions? Yeah. What if we have an unsymmetric matrix? So what's good about this is it works well for symmetric matrices. What's bad about it is many of the matrices you care about are not symmetric. Okay, and so what do? The answer here is a technique that is a very important thing called singular value decomposition. Okay, it's a different kind of a factorization technique, but it has the property that it will work over any matrix. It doesn't have to be symmetric. It doesn't have to be square. Okay, and the singular value of decomposition of a matrix factors it into an array of a matrix M, V, a matrix U, the matrix V transpose, and a diagonal matrix, okay, meaning that it's all the weights on the main diagonal, and it's not an identity matrix. There's going to be weights on along the main diagonal. Okay. So what's interesting about this? This is another one of these matrix factorization techniques. We factor it basically M into the product of two different matrices. Again, what am I going to think of this is going to be? This is going to be an N by N matrix mix. This is going to be an N by N matrix. The last one is going to be an N by M matrix. So the final matrix is going to be N by M. Okay. The center matrix is just a diagonal, integers. Okay, and a diagonal matrix. Therefore, we could think of this as we have factored M into two matrices, if you wish. One, this UD, okay? And that's going to be an n by n matrix, and the other one's going to be an n by m matrix, okay? Now, if we just keep the rows and columns, okay, that are associated with large matrix weights, D, okay, then you end up having a similar phenomena like with the eigenvalue decomposition, okay? If we maintain only the rows and columns with large weights, then we will be able to compress the features with little loss, okay? And that is something called singular value decomposition. It's the same kind of an idea as before. You know, when we multiply a matrix, okay, we can kind of, we're multiplying the dot product of rows in one by columns in the other. If you multiply a row matrix, okay, by a column matrix, if you have an n by 1 matrix, you multiply it by a 1 by n matrix, or 1 by m matrix, you will again get a, an n by m matrix. The, you can reconstruct the product of any matrix as the sum of the outer products of every row and column here, okay? And if we do that, then we get a similar phenomena, similar ideas with the eigenvector decomposition. We can represent the product matrix, okay, as the sum of outer products. We know the importance of outer products based on that diagonal value D, okay? And we can then approximate the matrix, okay, by using a small number of rows and columns, just the ones that are considered most important. Any questions? Yeah.
Capital N. How can we find capital N in SVD?
How can you find capital N? Okay, so there is a matrix, again, I'm not sure, which is capital N?
The dimension of D matrix.
Okay, there exist these methods for doing the factorization. I'm not going to talk about how it happens. Let's consider it a black box. Okay, but the point is that every matrix can be factored like this, okay, and it has the interpretation where that middle diagonal vector in the middle has an effect of measuring how important each one of those outer products are, okay? Any questions? The way I like to look at it, the important thing is kind of why do you use something like this? This is kind of what happens when you take a matrix. I don't remember which matrix this was. It may have been my Lincoln Memorial. I think it was my Lincoln Memorial. Or maybe it was Lincoln. What is this showing me? Suppose I took the matrix and I did singular value decomposition. And I looked at, and I then sort the, the rows and columns, okay, according to that weight matrix D. If you look at what's happening here, if you'll notice can you look at this picture a little bit? What can you tell me about the most important rows and columns? Those are the ones that are on the left here. I don't know if you can see that. This is kind of showing you where, again, the ith column here is going to be the ith most important component, from most important to least important. This is going to be the corresponding vector on the other side, whose transpose, when you dot it, when you take the outer product with this, is going to define that outer product. what do you notice about the small components here? I don't know if anybody can see it well enough. Do you notice anything? Can you see anything in the picture? Okay, maybe where you're sitting you can't see it. But to me, when I look at this thing, the small high-valued components are very blocky. You see them all in large runs of red and blue. The less important components you see look much more like random noise. Okay? That's my interpretation of what I'm seeing here. As you look over here, you're seeing, what you call it? You're seeing things that look very blocky. What's that meaning? The first components are kind of if you have a blocky matrix that you're multiplying by a blocky vector, that you're multiplying by a blocky vector, it's kind of going to rough out the structure of what it's seeing. And subsequent components are going to add little details. That's the argument that says that you can throw out the smaller vectors with less change to the reconstructed image. Okay, and this is a way that you can now take your n by m data matrix and reduce it to a data matrix formed by only let's say the row or column parts. Okay, this here is showing a graph of, as we add more and more of these outer products, how closely are we approximating the matrix? And the more components we add, the lower the error is. But it should be clear that after a small number of components, okay, the error starts going down relatively slowly, meaning that you've kind of blocked out the structure here. Any questions? So this is what happened when I tried to reconstruct the Lincoln face from the 5 most important, okay, singular values. Okay, that means the largest 5. I got the largest 5 rows that I got on the as per that matrix D, the largest coefficients. And as you can see that after only 5, by reducing Lincoln from a 512 to 512 image, here I am representing Lincoln as a 512 by only 5, okay, values, times the other 5 vectors. So it would be this much data. This is what I got from for Lincoln. And as you can see, you can already see the big structure of him, even though you've reduced the amount of data in here by a factor of 50 or so. Here I'm using 50 singular values. Here I've reduced the the size of the vector by about a fifth. Okay, and you can see that the picture here is almost as good as the original. Okay, this again represents the difference between the original and what I get after using the first 50 values here. And as you can see there, the errors are blocky because the reconstruction is kind of blocky. The errors are more likely to happen at, strong changes of things. Okay? But basically, we have SVD is a great way to reduce the size of a matrix. And that means that if you have an input problem where you have an n by m feature matrix and m is relatively large, it can pay to do an SVD of the matrix and use the and use the compressed matrix that you get. Okay, and that would give you features that contain almost all the information of the original matrix, but with much lower dimensionality. Any questions about that? As far as I'm concerned, the important thing is to understand why this is a useful thing. Okay? You live in a world, we are used to living in a world where we have n rows and a lot of features. Building a model on a lot of features, okay, there's a lot of ways you can go wrong. If instead you can reduce it to a matrix on only k dimensions, okay, then if this has almost all the information of the original matrix, then this can be building a model on these compressed features can be more powerful than the original. Any questions about that? Yeah.
It's mathematically practical for big data set. For example, if n is 15 million, can we use this method?
Okay, so the question is, as this gets larger and larger, okay, so what is I think what you're asking is, what is the runtime complexity of a method like this? So I believe that this is kind of like all the other graph matrix operations, where generally speaking on an n by n matrix, it will take something like n cubed time, okay? Now, so that on an n by m matrix, it's probably something like nm squared or something like this. Now, is that large? Notice that n by n was the input size of the original matrix. When you're telling me you're using 15 million rows, if you're telling me you have a 15 million by 15 million matrix in your main memory, I'm saying you probably don't. Okay? Normally, I mean, again, you want to work now, can you apply this on a large data set? That's right now really what the question is. The question of this is that this is not a linear time procedure, okay? It is something that grows faster than the input size of the matrix, okay? Which does mean that it gets to be computationally expensive for large things. Now, how big a value of n can you run this on comfortably? We have run it, I know in my lab, we have run it comfortably on things with like 30,000 items. Okay, that seems to be what I'm remembering in my head. There are other matrix approximation methods that are more efficient. They may not be as good, okay? But generally speaking, for a reasonable sized data matrix, where you've got, tens of thousands of rows and, a large number of features, typically in a data matrix, if you have 10,000 rows, each row is an example. The number of columns is typically less than the number of rows. Does that you kind of agree with that? That typically, if you have a housing data set, there are a million houses out there, there's only a certain number of properties. These matrices are not so large often that you can run an SVD on it in a reasonable amount of time.
Can we choose? Is it a good idea to choosing randomly, for example, 30,000 out of 15 million, and then run SVD to find which feature is important, and then back to.
Okay, so what you're saying here, you're again concerned about very, very large matrices. Okay, you're saying what happens if it's so large that I can't run a run an SVD on it. So first of all, I'd say I think about this in a couple of different ways. Generally speaking, if you have a huge data set where you've got millions of rows, you probably don't have that many columns. Okay? If you don't have that many columns, then it's less important to try to compress it. Okay? So in general, are people pining because they have millions of rows, and if you have thousands of columns and millions of rows, you have a ridiculously large matrix to begin with. You probably can't work on it. Okay? The question now says, well, what if I do have such a thing? How might I be able to compress my matrix? Okay? Well, one idea would be you pick a bunch of, you're saying pick a bunch of rows randomly. Sorry about that. Pick a bunch of rows randomly, and then do singular value decomposition on that. That will sort of tell you, if you interpret it right, which were the rows and columns that are kind of important. Which are the columns of data that are most important? And maybe use that formula to compute it on the rest. That can be a reasonable thing, but let me interpret it a little differently. What you really might want to do, if you have a world where you've got a huge number of rows and a modest number of columns, if you want to reduce the dimension of the matrix, what might be an alternate way of doing that? Well, I would be curious to compute essentially the covariance matrix of the columns. If you have a bunch of two columns, let's say, that are very, very highly correlated with each other. Let's say you have the height, and let's say something that was height in shoes and height without shoes. These numbers are going to be very, very correlated. If you know they're correlated and strongly correlated, and you want to reduce the dimension, you're safe dropping one of the correlated fields. Okay? And so if you're asking me what would be my preferred way of reducing if I have a data set where I have a large number of rows, a certain number of columns, I would want to look at the covariance among my features to figure out which ones are kind of important and which ones aren't. Okay? And that would be my first step to do it. What you're proposing is kind of sort of a way of kind of doing that. You're taking a sampling of these things. You're trying to figure out which features are kind of implicitly important. Okay? But anyway, generally speaking, for reasonable numbers of rows, okay, you can do an SVD, and there are approximate matrix factorization techniques that will try to, that probably are better choices for very, very large data sets. Any questions? Any questions about why SVD is a good thing to be able to do? Okay? Okay, good. Okay, so now, any other questions about the linear algebra stuff? Hold on. Okay, so that said, what I'd like to do now is to talk about linear regression. Linear regression is something that you guys have used already in your assignments, okay? The basic problem was, suppose we have some target variable, which is the y here, and we have some data values, which are kind of the x, okay? Linear regression is basically trying to find, in the scatter plot of x and y, what is the line that best approximates the points? Okay? Why is this an interesting thing? Well, first of all, the line gives you a model to make predictions. If this was kind of the height for someone who weighs this much, if you wanted to guess how much does somebody who weighs this much, how tall are they, that prediction is kind of given by the line that fits it. Okay? So linear regression is a way of taking a bunch of observations and building a model of how y varies as a function of x. And it tries to basically enable you to make a prediction of what the value of y is as a function of x. And we seek the line, okay, that kind of best fits it, okay, that it, generally minimizes least squared error. Any questions about that? Now, how do I think about first of all, linear regression? Why is linear regression a good thing, or a good reasonable model, okay, or a good first model to build from any data set? One is that linear function relations are easy to understand, okay? In a linear, relation, it would be saying that your weight is going to be, something times your height, okay? We know that as your height goes up, your weight's going to go up according to the model. That's relatively easy to understand. A lot of things have linear relationships with them, or at least a lot of, let's say, operations in the world. There kind of is a linear model kind of explains what's going on. Does your income increase linearly with the amount of time you work? Do people believe that? Do people not believe it? If you are paid by the hour, your income grows definitely grows linearly with what you work. It's your pay times the amount of pay times the amount of hours that you work. Okay, so for hourly workers, this is a good thing. In general, does income grow linearly with the amount that you work? Many people are not paid by the hour. You guys are all hoping not to be paid by the hour, okay? You will be working for, hopefully, a reasonable work week, and the better people will get more. But it's not clear that the guy that works the most hours gets the most money. But generally, there's a correlation, right? But there's a reason why you can think of that as being linear, and linear is a reasonable thing that happens. Do housing prices grow linearly with area? Okay, if you have a house that is twice as big, do we think that the price of the house should be twice as much? Not necessarily, but is it grossly appropriate? Does it seem like a model like that is crazy? Or is it right? It's not completely appropriate, okay? In most places, I would think, the housing price there's probably a decrease as the area gets bigger and bigger, right? How much more are you willing, once you have a large house, how much are you willing to pay for twice as big a house? You don't need twice as big a house, and it may be cheaper to build, extra area into the house. In New York City, it turns out that the housing prices generally grow superlinear with area. A 2-bedroom apartment costs more than twice what a 1-bedroom apartment does. Okay? But grossly, it's clear that the direction is right. People will pay more for more area. They may not, it will grow, it goes in the right direction. It may not be linear, but I think that's a gross approximation of what's going on. Does your weight increase linearly with the amount of food that you eat? If you eat twice as much food, will you weigh twice as much? You're saying no? It's probably not. Will you weigh more if you eat twice as much food? The answer is yes. Do I think it's going to be twice as much? Probably not. Okay. But frankly, I don't really know that. Okay. you know, so what I will say is that linear models are generally approximations to reality. But if you have reasonable features, they're not crazy approximations to reality. Okay? Now most functions are not linear. One line I heard is if you have a function and you want that function to be linear, the key is to only measure it at 2 points and interpolate. Okay? But if you have more and more observations, it's probably not going to be exactly linear. But linear is a simple case and a useful case. Any questions? Okay. So what is the way that I think about linear regression? Okay? Trying to find the best fitting line to a bunch of points. What is it that makes that hard or interesting? Okay? It's not the fact that we're trying to approximate a bunch of points by lines. You guys are familiar with linear solving systems of equations. What do you do when you solve system of equations? You've got a bunch of different equations, and you want to find the point that is in common on all of those lines. Okay, each equation defines a line. The solution to a linear system is the point that lies on all the lines. If we think what linear regression is, the problem of linear regression is really that we seek the line that lies on all the points. Okay? There are two differences between solving linear systems and regression. One is that we swap the word line and points, and the other is that the line that we're seeking isn't lying exactly on all the points. Okay, when you're solving a system of linear equations, you're seeking the point that lies exactly on the lines. Now, this is what makes the regression kind of a harder or a different problem. It turns out that there is a geometric duality transform that is relatively simple, that takes points to lines. Okay? So here, suppose in the plane we have a point ST. We could interpret it as a line where the slope is S and the intercept is minus T. Okay? You can imagine this as moving between one space and another. So here, if you look at this case, here we have a situation where I've got two lines and I've got 5 points on those lines, and I colored the points in a certain way. If I do this duality transform as before, every point in here is going to become a line on the other space. Okay, so if you notice, this thing had one red point. In dual space, that corresponds to one red line. This corresponds to, I had one blue line. That's going to correspond to one blue point, okay, in dual space. 2 points on, on that line are going to correspond to two different lines in dual space. And you'll notice that there's an incident here where the two different points go to two different lines. Those lines pass through one blue point. That blue point corresponds to the blue line. Okay? Namely, every point that is on this line in primal space corresponds to a line that is that passes through the corresponding blue point, okay, in dual space. What does that mean? that means that here, the red line, if you follow what I'm saying, here, the red dot is the point that is on all these lines. This is kind of what you would find by solving a linear system. In dual space, okay, we get a line such that all the points corresponding to lines that pass through it are on that, are on that red line. What does it mean? Finding a point that is in common to all the lines in primal space is the same as finding a line that goes through all the points in dual space. So the problem of finding a line that goes through all the points is not harder than solving a bunch of systems, a linear system. Okay? The interesting difference between solving linear systems and regression is that the points that there's error, that we need a line that best fits the points, not a line that goes through all the points. Any questions about that? Okay. So, how do we measure error in linear regression? We say that the residual error between a data value and the fitted line is going to simply be the value that we're trying to predict minus our prediction. Okay? So the residual, if we have a particular a fitted line, we have x, we have y. The residual is the difference between the prediction and the reality. Okay? The difference between the prediction, which is the point on our line, and the actual point. Least squares regression gives us the line that minimizes the sum of the squares of the residuals. Okay? And why does it do that? Why do we like that? Well, first, we like it because there is a nice closed form for it. So we can find the coefficients of the line that minimizes the square of the residuals. The other thing is that by squaring the residuals, okay, it means a positive error and a negative error don't cancel each other out. Okay? So the least squares criteria is a useful metric for these things. Any questions? How do we find the least squares? How do we find the coefficients of the line that best fits a given set of points? Well, the vector W, the coefficient vector, okay, can be obtained through linear algebra, okay, if we have a world where our points, okay, we have n points in m dimensions, okay, and we have a target vector b that's containing kind of like the y values, what we're trying to predict, okay. We would like to try to figure out what is the coefficient vector w such that the points times the coefficients best fits the targets. According to this formula, the coefficient vector is we take the data points, we transpose them, multiply them by a, take the inverse of this. This now is a covariance matrix. We take the inverse of it, we multiply it by the transpose of the points, and multiply that by the target values. If you work this right, this gives you an m by 1 matrix. That's what we would want the coefficients to be. We want a weight to multiply each one of the features by, such that the sum of the, for any given point, the sum of each of its dimensional values times the appropriate coefficient, the dot product of those things, approximates the target. Okay? Any questions? If we interpret this in one dimension, okay, what linear regression is doing, I think, becomes a little bit clearer. Okay? The best fitting line in one dimension is y is going to be an intercept plus a weight times the variable. What is the slope of the best fitting one-dimensional thing? Okay. It turns out if you look at it, if you look at this formula, you'll see things that are, what is it we're going to have here? The sum, the slope of this is going to be the sum over all the points of the difference between that point value and the mean. Okay, times the difference in the y's, the difference in the x values and the difference in the y's. We saw something like this in a correlation, right? If we wanted to look at what was the correlation of variables, we had something where we were subtracting basically the correlation between x and y. We wanted it to be the case that when x was high, y was also high. Okay, so we had a term looked like this. When we normalize it, we're normalizing it by something that's the sum of the x, of the squares of these things. This is analogous to a variance. Okay. When you solve this thing, it turns out that the slope is going to be basically a the correlation coefficient of the two values, the target variable y and the independent variable x, times the standard deviation of the y's divided by the standard deviations of the x's. So what's the idea here? The coefficient here is going to depend upon the correlation between the two variables. What if there was no correlation between the two variables? What if x and y had nothing to do with each other? What would be the best fitting line? Suppose we had a world where we just had random points. What should the best fitting line y be? Okay, the slope should be 0, right? Because if it has no dependence upon x, then you wouldn't want it to have any dependence on there. So if they are uncorrelated, the slope is going to be 0. If there is a very, very strong dependence, if it's a positive relationship, a positive correlation, you want the line to be tilted upward like this. If there was a negative correlation, meaning that when x got larger, y got smaller, you want a line with negative slope. So that is why there is a dependence on correlation. The scaling, though, of the actual slope depends upon the relative variance of these things. If the y values were measured in a very, very small unit, like let's say millimeters or something like that, you could imagine a world where the range of possible y values is large, the range of possible x values is small. That's going to change the slope of the line. If the x values were measured in miles, if we convert it now to meters, the x value is going to grow like that. The slope of the line would therefore retreat. So this is basically saying we're letting the correlation set the direction of the line, the direction of the slope. And the scales of it depend upon the range of values, which is kind of captured by the standard deviation. Any questions about that? If we think about that, how do we interpret the what you call it, the intercept of the line? It turns out one point that is always on the least squares fit is the mean of the x value. If you take the average of the x and the average of the y, the point x bar, y bar is going to always be on the on the line, on the regression line. And so if you have a point on the line and you have the slope, you can figure out what the intercept is. Any questions? Okay, and these are basically saying what that's about. I think I've said these kind of things. Now, where does that formula come from? Okay, it turns out it comes from the following. If we want the best fitting coefficients, the best fitting for the line, we need to have the property that if we have the best fitting line, there is no way that we can move that line and have it fit the data points better. What does this mean? It means that if we look at the errors, okay, in the predictions, okay, namely the target values minus the predictions, if W are the coefficients, this error vector, it turns out, has to be orthogonal to the vector of each variable. If not, there would be a way you could show that there would be a way that you could come up with a better fitting line than W. If the error vectors are orthogonal, okay, to the predictions, then that means that the dot product of two vectors that are orthogonal is 0. This basically means that the error times the data for these things, the dot product is going to be 0. If you believe this, then this follows directly. We put, we multiply out the AT, we put this term on the other side, and, and we invert it. So this follows directly from algebra once you get this, this term set up. Any questions? Okay. So bottom line is, if you believe that there are, we now believe that there is magic that will enable us to, there's magic that will enable us to find the best coefficients for any set of points. Now, on your homeworks, you guys used linear regression for different things. The key to making good regression models is to realize that there are things you can do to your data matrix and things you can do to your target variables so that you yield better predictions. Okay, and so linear regression is a good technique, but the key direction, let's say, that you have that for now for us to think about is how do we pre-process our data to make it better? The first thing to note is that linear regression is very sensitive to outliers. If you look at this particular example here, okay, if we have a world where there are a bunch of points that have a pretty good correlation, okay, but there is an outlier, a point that's relatively far from the best fitting line. What do we know about outliers in linear regression? Well, because we are trying to find the line that minimizes the sum of squared errors, this quadratic weight on the residuals means that outlier points, okay, have a disproportionate effect on the slope. If I have one outlier, the linear regression, the best fitting line is going to chase that outlier. If I move that outlier further and further away, the best fitting line is going to move in that direction. If I identify the outlier points, okay, and I delete them before I fit, I will end up with a potentially a much better model. Okay, it should be clear in this case that once I remove the points, the outlier point, that the model, that what's left has a much higher correlation, okay, between X and Y. That represents a much better fitting line. If I can find a way to identify outlier points and remove them in a principled way, then I can get a better fit. Any questions? How can you identify an outlier point for a possible in a linear regression model? What? One possible way is by visualizing it. But actually, that's not so good, come to think of it, because how many dimensions, when you were doing your homework, how many dimensions was your linear regression model when you were doing your homework? How many dimensions? Does anyone remember? Did you do something in 10 dimensions or something like, or more? Okay. Quite often, if you have 10 features, let's say, you would expect that you're dealing with something in 10 dimensions. You can't see something in 10 dimensions. In one dimension, I agree, you can say that's the outlier. So how can we identify what possible outlier points there are? Okay. If you're trying to fit a linear model, what would be a way that you might be able to see if there are outlier points? I would check the residual error. What was the residual error? On this point, even though the point was, if we had a world like the one that is on this picture, we had endpoints that were well behaved, one bad actor. Even though the line is chasing the outlier, it can't completely follow the outlier because it's got more points that are behaving well. The net result is that this point is going to have the largest residual, even in a fitted model, between the target value y and our prediction for it. If we look at the points with the biggest residuals, those are the ones that are most likely to be the outliers. Okay, and so if I had to remove somebody to try to come up with a better fit, those are good candidates to remove. Should I remove it to get a better fit? Well, that depends, okay? It's a question of, I would look at those examples and say, is there a reason why they are outliers, or are they real things? Am I going to want to try to predict those points, or is that really just kind of a bad data set, something that's really kind of weird? Whether to delete the outlier is a judgment call, okay? But should be clear we can identify which are the points that have the largest residuals, okay? And we can then look at what happens if we delete the points with the largest residual. How much better does the model get? Okay? Does the model get a lot better for other points? Is there reason to believe that the points that we deleted are things we shouldn't be interested in? That's the kind of thought process that you guys can go on in trying to figure out the model. Okay? Any questions? It should be clear that outliers have a big effect on the model. It should be clear you can identify them. The question of whether or not you want to remove them is now a judgment call. Okay, but what you could do is remove them and then refit the points and yield a different, possibly better model. Any questions? Now, one problem that people have with linear regression is they complain that it's linear. Okay? Linear regression is going to fit, what you call it, a line to the data set. Okay? It's not going to fit a higher order polynomial. It's not going to fit an exponential. It's not going to fit a lot of other things. Okay? That said, linear regression is perfectly good at fitting nonlinear functions. Okay? Provided you augment your data set with the nonlinear terms. Suppose, let's say, I wanted to, I had a bunch of circles. Okay, let's say that I had a bunch of circles, and I knew the diameter of each circle, and I knew its area. Okay, you can imagine a world where you're trying to produce a what is the area of a circle as a function of its diameter. Now, does the area of a circle grow linearly in the diameter? No, okay? You're saying the ancient Greeks did this thing, and they knew that, in fact, it grew as a square, a function of the square of the diameter, right? Like it was a square of the radius, right, which was half the diameter. Now, how could we find a better approximation? Could we have used linear regression to come up with an accurate formula for area if all we were given was diameter? Well, right now, the matrix that we were given just had the diameter. We had a bunch of points, and we had the area. That was our target. What if I also add the diameter squared? What if I add the diameter squared as what you call it? If I as another column in my data matrix. Actually, I'm not feeling I have enough room to write this here. Okay. What I'm claiming is, if I have I can always take my matrix and add other columns. If I have an n by k data matrix, I can always add more columns to it, okay? And now try to fit what is the best fitting line going through the data where I have the original columns plus extra columns that I add. If I want to fit a quadratic function, if I add x squared as a column, if I have a field x, if I can take my matrix and add another column, x squared, and if I do that now, when I do a linear fit between y and the matrix where I've got x and x squared, if the function, like the area, really is a function of the quadratic term, the linear model will find the best weights for this column. In this case, it might be pi over 4. And this column, it might find the best weight for might be 0. Does everybody see that if I know what the nonlinear terms that I want, I can augment my data matrix by as many nonlinear terms that I think might be interesting. And then a linear fit in these nonlinear terms is going to be a nonlinear fit. Okay, and linear regression can find the best fitting nonlinear fit where you of any set of nonlinear terms you specify. Any questions about that? Okay, this is an important thing to be able to do. Okay, you can augment your data matrix by any polynomial functions of your input variables. You could add x cubed, x squared. You could add the square root of x, which would be a sublinear term. You could add 2 to the x. You could add log x. You could add 1 over x. Okay? If you want to get a nonlinear fit by adding nonlinear functions of your input variables, okay, the best fitting line in these nonlinear terms is going to be the best nonlinear fit in those terms. Okay? So the good thing is linear regression is not limited to linear things. The bad thing is that you have to decide what variables to add. And if you try to add everything, you quickly will get, a huge number of variables. Once you have more variables than you have input points, there's no way that linear regression is going to do anything interesting. Okay? But if you have an idea what those nonlinear terms are, this is a good idea. Any questions? Okay. What other things can you do to your data matrix to make for a better regression model? One thing that turns out to be, a generally good idea is if you have variables that are over a different, let's say different and incomparable ranges, it can be good to replace the underlying variable by the z-score of the underlying variable. Let's say I wanted to predict how wealthy a country was based on what its population was and the fraction of the country that could read. Do we believe that a country is wealthier the larger it is? I think generally yes. Okay, each person is doing something to accumulate wealth. Do we think that the population is going to be richer, the higher fraction of them that can read? I think that's generally true. But notice what happens if you try to build a model where one of the variables was the population of the country and the other was a fraction of how many could read. Note that the population is a big number and the fraction is between 0 and 1. If we're going to try to bring this to a particular target, if these are going to have roughly similar effects, either C1 has to be very, very small, or the coefficient C2 has to be very, very large. Otherwise, the contribution of this variable is not going to be anywhere near the contribution of that variable. It turns out that for certain algorithms that people use to solve linear regression, that we'll talk about actually next class, it's bad if the variable ranges of different features are wildly different. If you reduce these things to z-scores are just linear transforms. And if you do use the z-score, then in a z-score, the variables are going to be mean of 0, standard deviation of 1. They're going to be directly comparable, okay? And therefore, the coefficients of those variables are going to be comparable, okay? And it makes the model easier to interpret. Any questions? Okay. One issue that comes up when you're building models is that by linear regression is that if you have features whose distribution is different than the distribution of the target variable, it ends up giving you strange answers. Okay? Suppose, let's say, we wanted to predict somebody's education. Okay, somebody's years of education. Here, Y is going to be the years of education. How many years do they go to school? If you get a PhD, you spend typically 12 years as an undergrad in high school and below. You spend 4 years in college and 5 years getting your PhD. The number of years of education you might have it's hard to get that number much above 19. Okay? If you wanted to predict, do we believe that people will get more education as a function of how rich the parents are? Generally, I think that's true. Okay? And certainly in certain countries, if the parents don't have any money, the kids never go to school. Okay? If you wanted to build a model where you were trying to predict years of education as a function of income, notice that if you have the target variable that you're trying to use, I mean the independent variable, if it was something that was power law distributed, something like income, note that a linear model can't really give a sensible answer to this. If you take someone like Bill Gates, their income is going to be, millions or billions of times the amount of income that a normal person might have. Okay? If you're going to try not to predict an error, Bill Gates' kids can't go to school for more than about 20 years, regardless of how rich Bill Gates is. If you have a power law variable here, okay, the coefficient that you've got to give it so that you multiply that income by, okay, has got to be extremely small to avoid an outlier of a very rich person giving a terrible prediction. Okay? So we need to find a way to normalize our variables to deal with, if let's say, what we were trying to predict was the distribution of years of schooling. What do you think the distribution of years of schooling are? Let's just think about this now. If in the United States, okay, what would you say is the fraction of the population with how many years of schooling from 0 to 19? Does anyone have a sense what that distribution should look like? Okay. No one has a sense of a distribution. What I would say is probably it's going to look like this. Relatively few people drop out at early ages of school. They don't drop out in 4th grade or 5th grade. So very few people are going to end up with 3 or 4 years of schooling. Maybe in high school, some people are going to drop out. By high school itself, when you graduate after 12 years of high school, there's a bunch of people who are going to stop then, right? Then there are 4 years of college. How many people do we think go through college? Okay, something like about 2/3 of Americans these days go to college. It used to be about 1/3. We expect that a fraction of them are going to graduate, relatively few are going to drop out during time. They're going to graduate. How many people are going to go to grad school? Relatively small populations. How many people are going to graduate with master's degrees? How many people will graduate with doctors? You probably end up with a distribution something like this. If you're trying to predict a function like this, okay, from a variable that is a power law distribution, where you have what? A very, very long tail, okay? You can't make this function out of things like this. So you need to normalize, okay, either the target variable or the independent variable in order to make use of income. The z-score is a rescaling, but it's a linear rescaling. The z-score of income wouldn't help you with this kind of a model. But maybe taking the log of the income would now give you a number that's kind of on a commensurate scale with the amount of years had. Okay? And so if you were trying to fit a linear regression model, okay, it is, you know, if the shape of what you're trying to predict is not a power law, if the features are power law features, you have to try to hit it with some kind of a normalization. Any questions? Okay. And again, as I said there, that's an argument that says that if you have what you call it, a world where there is, you know, the shape of the distributions of the variables are considerably different than the targets, that's an argument that you might want to hit it with a nonlinear transformation. Okay? Any questions? Okay. Okay. You know, this is an important enough point that I can see I've lost my train of thought. Let me actually end it over here. Okay. Any questions about this? Maybe I'll review that later. Yes.
Three or four lines, a line in some data, and another line, different W.
Wait, say that again. I'm not getting your point.
I mean, for example, if we divide our training data, then cluster them, and for each cluster we can pick a line, but not.
Okay, what you're saying now is a different idea of model. But again, what is the question here? The question is, what is another way that I might be able to deal with the fact that, let's say, incomes go into cover a very, very broad range. Okay? There are poor people, there are middle class people, there are very rich people. And maybe what you're saying is that they are all kind of different phenomena happen in these clusters of people. One possibility is I build a separate regression model for poor people. I build a separate regression model for middle class people, and I build a separate regression model for rich people. Would that be a way of dealing with the fact that something like income is highly not, has a power law distribution? I think that's what you're asking, right? So breaking the input variable, the input rows, the examples, into different categories and building a separate model on each category can be a perfectly reasonable thing to do. When is that good? That's good if you have a large number of training points. You need to have enough training points that you could afford to build a separate model for each class. Do you kind of agree with that, right? But if you have a world where you've got, a lot of training points, they fall into natural clusters, might it be interesting to cluster it and build a separate model for each cluster? The answer is yes. And that's one reason why we will talk about clustering a little later in the course, okay, as kind of being an important technique there. Okay, any questions? If not, thanks for your attention, and I will see you guys next class. And if anybody wants to talk about their projects, you can catch me now in my office. Okay, thank you.